Hello students, and welcome to topic 11 of alternative and renewable energy sources. The topics we will be covering is the wind calculations, worksheet 11. The activity is recorded and you are to work the activity along with the recording. On worksheet 11, we are to calculate the wind power density of wind at a speed of 10 meters per second. Wind power density is equal to 1/2 rho, the density, times the velocity cubed. Notice that the power of the wind is a function of the third power of the wind. The density of air is considered to be 1.225 kilograms per meter cubed. Therefore, the wind power density is equal to 1/2 times the 1.225 kilograms per meter squared times the 10 meters per second cubed. So the calculations give us the results of 612.5 watts per meter squared. The Bates limit states that we can only obtain 0.593 of the total wind power. Not all the power of the wind can be converted to useful energy. Therefore, the absolute most energy that can be captured from the wind is the Bates limit. Using this number, the power is equal to 0.593 times the wind power density that we calculated. And this is for a wind turbine blade that is 4 meters tip to tip. So we take the 0.593 times the wind power density of 612.5 watts per meter squared times the area that the blade of this traverses, pi times 4 squared, that's meters squared, so it's pi d squared over 4. So the power is 4,464 watts. We are to calculate the wind power density in pounds and feet. The density of air is 0.075 pounds per foot cubed. So to calculate the wind power density is equal to 1/2 times the 0.075 pounds per foot cubed times, and we have to convert the miles per hour to feet per second. So it's 30 miles per hour times 5,280 feet per mile times hour over 3,600 seconds. So it's 3,600 seconds per hour, and that cubed. We obtain 3,194.4 foot-pounds per second per foot squared. We know there's 550 foot-pounds per second per horsepower. We know there's 0.746 kilowatts per horsepower, which gives us 4.3328 kilowatts per foot squared. Now we have to multiply the wind power density times the sweep area of the 30-foot diameter wind turbine. So we take the 4.3328 kilowatts per foot squared multiplied by pi d squared over 4, which is pi 30 squared over 4, which gives us 3,063 kilowatts. Next, we are to use the Bates limit, so we simply multiply the 0.593 times the 3063 kilowatts and obtain 1,816 kilowatts. The Bates limit is the highest theoretical power we can capture from the wind. In reality, it's something less than that. So we look at slide 7 for a 2-blade high-speed horizontal axis wind turbine, and we obtain a coefficient of 0.47. This is what we use in our calculation instead of the 0.593. Notice that we go back to the 3063 kilowatts multiplied by 0.47 and obtain 1,440 kilowatts. The last calculation we are to perform is to estimate the speed of the wind at an elevation of 35 meters when we know the speed is 12 meters per second at an elevation of 10 meters. The location is on low grass. The shear exponent for grass is 0.14. Therefore, the velocity at 35 meters is equal to the 12 meters per second known at 10 meters at an elevation of 10 meters times the 35 new elevation over the 10 the old elevation to the exponent of 0.14, which gives us then the speed at 35 at an elevation of 35 meters is 14.3 meters per second. If there are any questions, please post them on eLearn Help Discussion.